Hey everyone, today we're going to be looking at how we do completing this square. When we talk about completing this square, we're talking about yet another technique that we can apply to quadratics. When it comes to our quadratic functions, we want to be able to state the properties of our quadratic function. And we know that we can do this just by looking at the quadratic equation itself. Now, when we do the completing of the square, we're able to get not just a few properties, but we can actually get nearly every property that we will need if we ever wanted to attempt to do a sketch of our quadratic function. So let's start off first of all by looking at our general quadratic equation, and then from there discuss the properties of our general quadratic functions. We know that a general quadratic expression has the format ax squared plus bx plus c, where a, b, and c refer to constants that can take any real number value. Now, we've learned of doing things like factorization and using the quadratic formula to help us to solve when a quadratic is equal to 0. And usually we use these to solve for our quadratic when we want to identify certain properties of our quadratic function, such as its roots. We can use the quadratic function itself to identify other properties, and we've even been able to determine the nature of a curve based on the quadratic function's coefficient of x squared. So when we talk about properties of our quadratic function, there are several properties which we are usually interested in. Let's discuss some of the properties of the quadratic function. So we started by talking about things like the shape of our quadratic function. When we talk about the shape, we're talking about the nature or what type of curve we have when we look at the quadratic function. Now, when it comes down to the shape of the curve, we know that our quadratic function, being a parabola, can take either one of two forms. It can either be a U-shaped curve, it can be an upside down U-shaped curve, and in these cases, when we talk about the nature of the curve, our nature would refer to whether or not it's a maximum or a minimum function. So we always need to know when we identify a maximum function curve and when we can identify a minimum function curve. So if you can recall a maximum function curve, you'll know that the maximum function curve is our upside down U-shaped curve. So this means it will have a maximum value and a maximum turning point. And we usually associate our maximum curve with a value for our coefficient of x squared as being less than 0. So anytime we have our x squared coefficient being less than 0, we know that we're dealing with a maximum curve. And this is what the curve should look like. Now, when we talk about a minimum curve, you'd be able to recall as well. The minimum curve is our U-shaped curve. And in this case, it's the opposite of what we would observe for the maximum curve. In the case of a minimum curve, our value of a is greater than 0. So if we have a coefficient that is greater than 0, a coefficient of x squared that is being greater than 0, then we have a minimum curve. So these are the two things that we would be interested in when we talk about the nature of the curve or the shape of the curve. Aside from the nature of the curve, we also identify things like the axis of symmetry. The axis of symmetry, as we would know, for a parabolic curve, such as the ones that we look at when we study quadratics, we're talking about a curve that has a particular point where we can observe a symmetric shape for our curve. So now we're going to talk about the axis of symmetry. When we talk about the axis of symmetry, we're talking about that line where our curve is going to be symmetric about. And this particular line occurs when x is equal to minus b over 2a. So we've learned about this before when we looked at our general quadratic function. So we know that when x is equal to minus b over 2a. This gives us the axis of symmetry for our curve. Our curve is symmetric about this point, and the axis of symmetry passes through a specific point on our quadratic function's curve, and that point being our turning point or vertex. And this vertex usually is dependent on what type of curve we have. So the vertex can be either a maximum or a minimum turning point, and based on the nature of the curve, if we have a maximum curve, it's pretty obvious we're going to have a vertex that is a maximum turning point. If it is we have a minimum curve, we'll observe the vertex being a minimum turning point. So our turning point is usually that point where our curve turns. So that very top point for our max curve, or the very low point for our minimum curve, these points are where we would observe the vertex or the vertices of our respective curves. Now each quadratic function only has one turning point, right? It only turns through one point on the graph, and that is that vertex. So once we can identify the type of curve that we're looking at, we'll be able to identify whether or not our curve is going to have a vertex that is at the top or it's going to have a vertex that's at the bottom. The value for the coordinates of our vertex usually come from the lowest value of the function and the value of our axis of symmetry. So this leads into yet another property, whether or not our function has a minimum or maximum value. And this minimum or maximum value refers to, in the case of a max function, it's that highest value that the function can take. And when it refers to a minimum value, we're talking about the lowest possible value that the function can take. So these can all be identified from our completion of squares form, and we can even identify the roots from the completion of squares form, because the roots are also part of the properties of this curve that we'd be interested in being able to identify. So now let's talk about how we do the process of completing the square so that we'll be able to see where the values are going to indicate things to us pertaining to the properties that we've just listed. When we talk about completing the square, we're talking about being able to express any quadratic function in the form a into x plus h all squared plus k, where a, h, and k are constants. So these can be any real numerical value. When we talk about this particular form, there are some things that we need to observe. One is that we do have a constant outside of our binomial product here. Our binomial product x plus h to be squared. If you can recognize the perfect square, or you can recall what the perfect square looks like when it's completely factorized, you'll be able to relate to this x plus h to be squared as that perfect square completely factorized. And then finally, we also have another constant here, this plus k, at the end of our expression. E, h, and k will give us the values that connect back to our properties. And when we have to express f of x in this form, we need to be able to recognize our coefficients and our constant. We need to be able to do simple processes of factorization and even arithmetic to help us with being able to move through the steps seamlessly. So let's take a look at this example. We're going to express the following quadratic in the completion of squares format. So we're going to express x squared plus x minus 12 in the form ax plus h squared plus k. And when we have done this, we're going to see what the values of a, h, and k tell us. So let's start by looking at our quadratic expression. So over on the left hand side here we have x squared plus x minus 12. And if it is I want to express this in the completion of squares form, I need to do a couple of things. So the first thing is I actually need to look at x squared and identify the coefficient of x squared. Now if the coefficient of x squared is 1, which is the case here, I can simply proceed to my next step. But if it is the coefficient of x squared was not 1, then we'd have to do things a little differently, where we'd have to start off by factoring out this value from all the terms in the expression. So the first thing that we're going to do in this case, because our coefficient is 1, we're actually going to force fit this into a perfect square form. Now, x squared plus x doesn't look anything at all like a perfect square, right? X squared plus x minus 12, in fact, is not even a quadratic expression that will factorize into a perfect square. This is what I mean by we're going to force it to resemble a perfect square. And to do this, here's what we're going to do. We're going to start off writing a binomial expression raised to the power of 2. We start off with x because our function is in terms of x, so this is why we know we're going to start with x. The next thing we're going to do is look at the coefficient of our term in x. And here we'll notice that the coefficient of this particular term is positive 1. So if I want to express this little perfect square that I'm doing here, what I'm going to do is take half of the coefficient of x, and I'm going to write that in my binomial. So half of 1 will give me positive a half, and now I have my perfect square piece. So it looks like a perfect square, just a little fraction in there, but it looks like a perfect square. Now I'm not done as yet, because look at this format. It's a into x plus h squared plus k. So the a is already understood as 1 here, but when we do this, there's some change that's happening. First of all, minus 12 remains because we haven't interfered with it. We haven't done anything at all. So let's just rewrite this minus 12 here. But from forcefully fitting this into a perfect square, we've made a change to the system, right? And we know that equations, we need to always maintain the homogeneity of the entire equation by ensuring that if we add something somewhere, we're going to take it back out. So in the case of this adjustment here to force this into being a perfect square, we have in fact added in something that doesn't belong. And how do I know that? Well, if I were to expand this perfect square, which I will do, if I expand it, this is what I'll end up getting. So I'll have x squared plus x plus 1/4. Alright, so this is what this binomial will look like when I expand it out. Now, the x squared plus x remains because this is what we wanted to put in this perfect square form. But this positive 1/4, it didn't belong to the original expression, and we have to remove it because whatever doesn't belong needs to be removed. So this is the reason why after writing the minus 12, the next thing we need to do is take away what we've introduced into this system. And what we've introduced is the square of the half that we've put in that binomial, and that's why we're going to subtract out minus a half squared. So when we simplify this half squared, we'll get that 1/4 and be able to remove it. So that way, when we simplify this entire statement, what we get in this particular form will in fact be equal to the x squared plus x minus 12. So what we're going to do now is simplify the constant that we have at the end here, and we'll be able to express this particular quadratic in this format. So from here now, I get my perfect square, x plus a half, all to be squared. And now, simplifying, I have minus 12 minus a quarter. And then working this out, I will get my constant at the end here simply being 49 over 4. So now that I've simplified this minus 12 minus a quarter, I get minus 49 over 4, and that there expresses my quadratic expression in the desired form. So this is in the form a x plus h squared plus k. So what we're going to do now, we're going to learn to identify a, h, and k, and we're going to see how these values help us with identifying the properties of a quadratic function. So when we talk about a, we're talking about the coefficient of x squared from the beginning, all right? But that value will normally be written outside of our binomial expression. So we're going to state a, and a is equal to 1. Now, we know from before that the value of a usually tells us the shape of the curve, whether it's going to be that U-shaped curve, or it's going to be the upside down U-shaped curve. And based on the value that we've gotten here, this indicates to us that we have a minimum turning point or minimum curve. Alright, so this is a minimum curve simply because a is greater than 0. So we have a minimum curve, and that's our first property down. We now know the nature of the curve. The next thing that we can identify from this particular format is the axis of symmetry. The axis of symmetry, which we learned before, was minus b over 2a. This value of h, when we state h from the format here, all we have to do is take the negative of that value and we'll get the axis of symmetry. So x is equal to minus h, and it's the same as saying x is equal to the negative of whatever is this value here. And that's how we will get that our curve has an axis of symmetry of x is equal to minus a half. We'd get the same exact thing if we used this format, because h is equal to b over 2a. From here, I can state my axis of symmetry, and this value of x as well also corresponds to the x coordinate for our vertex. So before I get into the vertex, let's talk about the maximum or the minimum value of a function. We know that if we're dealing with a maximum turning point curve, we're going to have a maximum value. And if we're dealing with a minimum turning point curve, we'll have a minimum value. So in this case, because we're dealing with a minimum curve, we have a minimum turning point, so therefore we will have a minimum value. And to get this minimum value, we actually look at the value of k. So the minimum value of our function, in this case, comes from the value of k, which is minus 49 on 4. So we have the nature of the curve, we have the axis of symmetry, we also have the minimum value of our function. Using the axis of symmetry and the minimum value of the function, pairing them up, we can state the vertex for our curve. if I wanted the coordinates of the turning point or my vertex, what I'd write here is that my vertex has coordinates minus HK. I have the values, and all I have to do is just write them as a coordinate. So this means that my vertex is minus a half minus 49 on 4. I can use this format as well if I wanted to identify the roots of my quadratic function. So I don't need to only do roots from solving using quadratic formula or factorization, but I can use this format to get the values for my roots. So let's see how we use this format to solve and get the roots of our function. Since we're able to express our quadratic function in the completion of squares form, we can actually use this to help us with finding the roots of our quadratic function. Let's see how we actually use this format to find both values of our roots. We know that for a quadratic function, the roots exist and both are real and sometimes real and distinct depending on the type of curve that we have for the quadratic function itself. In the case that we're looking at here, we can tell that this function has two roots simply because it's a quadratic. Both roots are going to be real and distinct. We can actually do this and confirm this by using our discriminant analysis. But we're not interested in that part. We actually want to see what are the value of the roots. We want to get both roots. So we start off by stating our quadratic function is equal to 0. Just like if we were going to solve using factorization or quadratic formula, we have to remember that the roots occur when the function is equal to 0. So when f of x is equal to 0, in this case, we're going to use the completion of squares format instead, and we're going to put this equal to 0. At this stage, if we want to solve for x, we need to remember that we need to be able to transpose. So in this case, I want to solve for x, and I have to begin my transposition, first of all, by eliminating this minus 49 on 4. So to do this, I can add 49 on 4 to both sides of my function, and this will give me that my perfect square of x plus a half squared is equal to 49 on 4. From here, I need to square root both sides of my quadratic function so that I'll be able to simplify, and eliminating that power will help me with getting to solve for x. So square root of 49 on 4 will leave me with 7 over 2. Now, before I proceed, here's something that I need to remember. When I take the square root of a number, any number, that square root can take either one of two values. The square root can be positive, as I've written here, or it can be negative. So I must always remember this whenever I am doing this particular form, because I have to remember that a quadratic has two roots, whether they be real and distinct, real and repeated. So I include the plus or minus so that I remember that I'm considering both the positive 7 over 2 as well as the negative 7 over 2. And once I have these correctly stated here, when I try to solve for x, I'm going to get those two values for my roots. So at this point, I need to get rid of this positive a half. So I'm going to subtract a half from both sides, and this is going to give me two cases. The first case is when I subtract a half from a positive 7 over 2. And the second case, when I subtract a half from a negative 7 over 2. So let's solve for x. When we solve for x, we're going to get 7 over 2 minus a half leaves us with 6 over 2, giving us 3. And when x is equal to minus 7 over 2 minus a half, we're going to get that x is equal to minus 8 over 2, which simplifies to being x is equal to minus 4. So we get the answers for our roots, our two roots, one being x is equal to negative 4 and x is equal to a positive 3. And those are the roots of our quadratic function. So from the completion of squares form, you can get absolutely everything you need when it comes to sketching your curve. You can start with getting the nature of the curve. You can identify whether or not you're going to have a maximum or a minimum curve. You can find the axis of symmetry, so you'll know where your curve is going to be symmetric about. You can get the maximum or minimum value of your function. You can state the coordinates for the vertex of your turning point, your vertex or turning point, and the last thing that you can do using this form is getting the roots of your quadratic function. And that's essentially how you use the completion of squares to obtain the properties of your quadratic function. Alright, so now what about the case where the coefficient of our x squared term in our quadratic function is not 1? How do we treat with that particular case, and how do we write it in the completion of squares form? Well, let's take a look at an example of a quadratic function where we have a coefficient of x squared being something other than 1. What if we had a quadratic function such as let's say we wanted to express this in the form ax plus h all squared plus k if we were to express this in the completion of squares form, here's what we're going to do. We're going to begin, first of all, looking at the coefficient of x squared. Now, if the coefficient of x squared is definitely something different than 1, we're going to factor out that coefficient from all the terms in our quadratic expression. So I'm going to begin by factoring out 3 from every single term in the quadratic expression. Now you might think to yourself, but you can't factor out 3 from everything inside here. Some of these things aren't even multiples of 3. However, you need to remember that in this case, factoring out that 3 means that all we're going to do is divide every single term in the expression by 3. So this will give me 3 x squared being the only term that has a coefficient with a multiple of 3. X squared is here. Then these are going to be fractions. So we'll have 7 over 3x plus 2/3. What do I do from here? So what do I do from here? The next thing I'll do, this piece here, although we have these fractions, this looks a lot like the quadratic we expressed in the completion of squares form earlier, because the coefficient now of x squared is 1. So you can say to yourself that the objective of this first step is to bring the quadratic to an expression where the quadratic now has a x squared term where the coefficient is 1. And From there, we're going to just follow the same process that we did before. So the next thing that we need to do here, we're not forgetting this 3 outside, because this 3 is going to be important coming later down to the closer to the answer. Now I'm going to put this in that perfect square form again. I'm going to write a binomial raised to the power of 2, and x, because my function is in terms of x. Again, look at the coefficient of the x term in this expression. So we're looking at the one that we just factored out this 3 from. We're going to look at this coefficient, and I'm going to take half of this coefficient. Now, if fractions tend to be a challenge for you, just work it out to the side and you'll be able to get the answer. So here, when I take a half of my x term's coefficient, I'm going to get 7 over 6. Right, and just to confirm that, remember it's 7 over 3 by a half, because you're dividing it by 2, so you can say it's the same as multiplying by a half. And 7 over 3 multiplied by a half leaves us with 7 over 6. Okay, so I'm not done as yet. Just like before, we're going to write back our constant, which in this case is a positive 2/3, because we haven't done anything to that particular value. The next thing that we'll be doing is considering what we've added into this equation, into this expression, that is with this change that we've made. I've made a change here and I need to subtract out that change. I need to make sure and remove it. So what I'm going to do is remove this 7 over 6 squared, and that's how I will have minus 7 over 6 to be squared. Now, something that commonly happens when students are working out this piece is that they forget that it's always going to be a removal of whatever change has been made, regardless of what sign you see here. So it's always going to be subtracting out some change, and you do not at any point in time square the numerical value with the sign included, because this will now change the entire answer. You will not get the correct response that you're supposed to get for Q. So always remember, it's permanently a subtraction of whatever you've added into the system, and never square the numerical value with this sign. This will completely alter the answer you're supposed to get. So from here now, I just close off this curly bracket, and all I have to do is simplify my constant, and I'll actually have, that perfect square format, and I'll just have one other thing to do before I get the final result. So let's work out our constant for key. Everything else remains the same. We're only focusing now on working out the value of key, and this gives me plus 2/3 minus 49 over 36. So again, if fractions tend to give you a lot of trouble, you'll want to remember to do the working separately, just to verify that you are getting the correct answer. Now you're subtracting 49 over 36. So here we're going to get a negative result, because we're subtracting 49 over 36 from 2/3. So this will give me, so if I were to work out what this is, 2/3 minus 49 over 36. This works out to be 24 minus 49. And if you remember directed numbers, we'll be able to get this answer quite easily. So let's find the difference between 49 and 24, which leaves us with 25. And our answer is going to be a negative, because 49 is larger. It's minus 25 over 36 is our result. So we put in the next line, and notice I'm not skipping this 3 outside here. You want to always remember to keep writing it, because if you only forget that 3, you're going to get a completely different functions properties instead. So now I'm going to write minus 25 over 36. So while we might be tempted to say, well, we're done. We have A, we have this, we have that. This is not the final result. What you actually have to do now is multiply everything within the curly brackets by 3. Meaning that I need to multiply 3 by my perfect square, and then also 3 by minus 25 over 36. So just like you would have done your expansion of binomials using your distributive law, you can look at this piece as doing the same, except inside of your brackets you have a binomial expression all by itself as one of the terms. So what I'll get in my next line is 3 times x plus 7 over 6 all to be squared. So this is the first thing that I'll get. And then 3 times minus 25 on 36. This is going to simplify to give me minus 25 over 12. Alright, so this now is in the form that we desire, our completion of squares form. And from this we'll be able to state things like our nature of our curve, the axis of symmetry, the minimum value or the maximum value as the case may be. In this case, because we have a positive coefficient of x squared, it's definitely a minimum curve, it's definitely going to have a minimum value. We can say the coordinates of our minimum turning point, and we can also use it to get the values for the roots of our quadratic function. So this is how you would do your completion of squares if you were given a quadratic where the coefficient of x squared was not 1. This brings us to the end of our video. Thank you very much for watching, and I hope this has been very informative for you.